Hello and Namaste. My name is Sunil Laudari, and the title of my presentation is ESO 137002, a RAM pressure stripping galaxy with very little star formation in the tail region. As my research is all about galaxy, let me spend a few minutes about the environment as it plays an important role in the evolution of galaxies. So galaxies are associated with clusters and groups. Galaxy clusters, they are the large gravitationally bound structures in the universe. So to the left is the image of Coma cluster, which shows hundreds of galaxies with very different morphology and sizes. They are massive. They contain large fraction of early type galaxies and irregulars, mostly around the cluster core, and relatively small fraction of late types in the outskirt. So here in the image you can see like NGC 4921, NGC 4911, which are spirals galaxies. They are on the outskirt of the galaxy cluster, whereas we have NGC 4889, NGC 4874 lying near the cluster core. Uh, Also, we know early types contain very little cold gas and suppress star formation, and late types are rich in cold gas. And this shows there is some interaction with the intercluster media called the ICM that transform the properties or morphologies of galaxies. And also, we have a image on the right, which is a galaxy group which contains very few number of galaxies. They are less massive. And also, as I talked about ICM, which fills the space between galaxies, they are hot, mostly radiated in the X-ray band. So the middle panel here is a bullet cluster with X-ray emission in pink and optical in blue. So the ICM density is very low here, and the temperature is very high. So the energy is mostly radiated as Bremsstrahlung radiation. As I talked about galaxy environment in previous slide, there are currently different mechanisms that affect galaxy environment and in turn affect galaxy evolution, like heat conduction, viscous turbulence, galaxy-galaxy interaction, to name just few of them. But I want to focus only on ramp pressure stripping, which is also one of the primary mechanisms that enriches ICM by removing cold gas from the galaxy. So the stripping occurs when the pressure exerted by the ICM overcomes the gravitational pull of the galaxy to its own gas or dust. So at that point, the dust or gas is blown away from the galaxy, making a long tail, which is now referred as jellyfish galaxies in the literatures. So here to the left is an equation of ramp pressure, where P and rho are the pressure and the density of the ICM. B is the velocity of the galaxy. Sigmas are the surface densities of the star and the gas itself. So when stripping occurs, there is sometimes sudden starburst, that is occurrence of new star forming regions. It might occur in the main body or mostly in the tail region before completely stripping, and the process referred as quenching. So they reveal long narrow tail with rich substructures like filaments, knots, or clumps. Here shown by middle image taken from Rudiger 2008. The 2D simulations in 3 panels shows the effect of viscosity with more clumpy structures for a higher viscosity. So now I want to play a short movie, a 3D hydrodynamical simulation of galaxies, which is on the right side. So here the evolution of gas is in weighted temperature map. So as galaxies interact the ICM, it forms long tails of cold gas, forming new stars or sometimes starbursts. So let's see. So here we can see eventually after 2 to 3 million years, it completely gets stripped of coal gas, thus starting a new star forming region. Many examples of RAM pressure stripping galaxies can be found in the literature. So from these papers, it is understood that RAM pressure stripping partially strips large spirals in Virgo-like clusters and completely strips dwarf galaxies and massive galaxies in coma-like clusters. To the left is the XMM Newton mosaic of Abel 3627 along with the main tail of ESO 3701, which is a close companion of ESO 3702, the galaxy that I am presenting today. To the top right is the zoom-in image of the same galaxy ESO 3701 with the X-ray emission from Chandra in blue and S-alpha emission from SOAR data in red. So these strippings has been occurred in all bands. Here are some images of ESO 3702 tails at different wave bands. The tail stretches from the nucleus to the downstream. As you can see, the images also show tail, or to be specific here, double tails in X-ray from Chandra, S-alpha and optical from SOAR data. Compared to ISO 3701 or other similar RPS galaxies, the tails are shallower. Certainly, our HST data provide deeper observation than the previous cases. Now I want to focus on ISO 3702, which is a late-type massive galaxy in the closest ridge cluster Abel 3627. It also hosts a CP2-like AGN. Some important properties are listed on the right side. It is currently undergoing ozone stripping, and the galaxy itself is viewed ozone, which makes it important in comparison with ISO 3701, a Phaeton galaxy with similar stripping. Other properties like star formation rate and tail length are small compared to ISO 3701. The left panel shows a composite image with X-ray in blue from Chandra and optical image from the HST data. Here the right panel shows close-up view in 4 ST bands and that I worked. Here the 275 filter, which is a UV filter, is less smooth compared to other filters, as we all know that dust extinction is high in shorter wavelengths. Again, the upstream or the north direction is dust-free, but many dust clouds and filaments can be seen around the nucleus and up to the downstream or the south region. An X-shaped feature is shown on the top right, which might be due to the possible gas fallback, a hint of ramp pressure stripping. We applied 2D image fitting algorithm called the galfit to make a model and residual images in 475 filter as shown by the two images on the left panel. The residual shows dust substructures which extends up to 14 kiloparsec from the nucleus to the south. The X-shaped feature and the isolated dust clouds shown by red boxes are likely gas fallback. We also applied galfit in F160 data. The residual image of 160 is shown by the right image. It shows the presence of X-shaped or peanut-shaped balls, and also not to be confused with the X-shaped dust structures that we saw in the 475 filter. Below is the table showing some important parameters like the half-light, radius, total magnitude that we obtained from the 160 galfit fitting. Now I want to show few results from my work, especially the color magnitude diagram that I extensively used to study star formation. On the upper right plot shows the color magnitude relations for the tail in blue and control in red, defined by our regions of interest shown by the left image. Sources that are detected in all bands are shown by diamond, and ones detected in the 475 and 814 bands are shown by the upper limits. By just inspecting the distribution of the tail and control sources, they do not show any strong star forming regions. Also, the 275 minus 475 color is a good age indicator, especially in combination with the 475. So we applied simple stellar population model called Starburst 99 with Krupa IMF and Geneva zero rotation track with 0.014 metallicity. The plot shows two tracks here, with and without extinction. Based on these tracks, we can put an upper limit on the mass of young star clusters in the tail, which is around 5.2 10 to the power 3 solar mass for 10 million years, and around 7.6 10 to the power 4 solar mass at 100 million years. The star formation is around rate is around 5.2 10 to the power minus 4 solar mass, which is actually very small compared to ISO 37001. So the total age of the star clusters can be estimated up to 200 million years. While the galaxy is much fainter in 275 than in 475, there are some compact knots and clumps revealed in 275 as shown in the left image. These are most likely young star clusters formed recently. Interestingly, all of these blue sources have dust clouds nearer, and some of them are immediately north of dust clouds. This suggests that the star formation of some of these young star clusters is triggered by the compression of ramp pressure. So we made a color magnitude diagram to study star formation. We again applied Starburst 99 with same metallicity and two tracks with and without extinction. Based on these tracks, we can put an upper limit on the mass of young star clusters, which is around 10 to the power 4 solar mass, and total age estimated up to 200 million years. The star formation rate is around 1.4 10 to the power minus 4 solar mass, which is significantly lower than the total star formation rate of the galaxy. I would like to conclude my presentation by these points. ISO 3702 is a late-type massive galaxy currently undergoing ozone stripping. It has an undisturbed stellar body but strongly disturbed ISM as shown by dust features. The upstream is nearly dust-free while the downstream is rich in dust, suggesting stripping is still in action in the south. Young star clusters in the downstream and nucleus are likely triggered by ramp pressure stripping. The isolated dust clouds without UV sources are likely evidence of dust fallback. Perfect prototype for studying age-on stripping because of the favorable combination of three angles: nearly age-on 3D disk wind angle, disk viewed as a nearly age-on, and much of the ICM wind is projected in the plane of sky. Thank you.